use logarithms, by the way, is, and you'll see this. This is all connected together in what I want to talk about today. But if we have really big numbers, then it kind of makes, or even actually really small numbers, taking a log of a big number or whatever takes a gigantic number and it brings it down to something a little bit more manageable. Okay, so to kind of get a feel for this, I want you to imagine, let's say, oh gosh, so one application that I think most of you guys are probably aware of, one that I expect for you to know, is this bad boy right here, what is known as pH. Okay, this is one application of logarithms. And pH, again, all of you have been in or are currently in chemistry, and so you've had some type of, exposure to this, I would imagine. But formally defined, a pH is a logarithm. Interestingly enough, it's actually the negative log base 10 of, all right, I'm going to give you some notation here. If you are confused by this notation, please ask my AP students. But no, I'm just kidding. I'll explain it. But I'm going to write it to you this way. So I'm going to say of the concentration of hydrogen ions. Now what the square brackets mean, guys, that is just a notation. It's like a math notation. It just means the concentration of hydrogen ions in molarity, okay? Which again, some of you may not know or maybe do know. So just to be clear, in moles per liter. So moles per liter is a concentration unit, and that's the unit that we use. But this is actually the definition. Okay, everybody good on that front? 100%, everybody fine. So let me kind of show you why this comes into play, okay? But this is, again, pH is actually a logarithmic scale. So, case in point, just to kind of put this in perspective, do y'all remember what is a neutral pH at least? What do y'all remember about that one? So, yeah, you remember it's right. So hey, you remember that obviously a pH of 7 is probably about neutral, right? Of course, that's only true if you're at 25 degrees Celsius. Don't you worry, Shane. We'll get there later. Now, they're having a panic attack right now. They think they only get AP Chem once, or one class every single day. That's not true. Do you remember what is a basic pH? Do you remember like a really high basic pH, for instance? 3. Yeah, it kind of goes up to 14. So the basic region of things. Yeah, 13, 14. 14 is freaking ridiculous. We'll learn why. But again, I'm talking about pH scale. So this is your basic side of things. And then obviously, guys, if you go the other way, so if you go to really small numbers, right, you're going to get your acid. Okay? Now, where the scale comes from, like I said, are the outputs of this. Right? So, truth be told, again, if these are your pH values, truth be told, really what it actually is this. So, if you imagine concentration, okay, concentrations are actually, when we're talking about the concentration of hydrogen ion, are traditionally very small numbers. They're actually not big numbers. They're freakish, like very itty-bitty little numbers. So case in point, if you have, let's say, a very, very, very small concentration, like would y'all agree 10 to the negative 14, that's freakishly small. Right? That's really, really small. That's ridiculously small. So, all that being said, what chemists realized would probably make more sense in terms of just numerical values, if you want to think of it this way, is if we take the negative log of that number, let's do that over here. So guys, if we did the negative log, again, base 10 of 10 to the negative 14. Everybody with me there? Well, if you don't mind, eyes up here, I'm going to do something. I'm going to get rid of this negative for a minute. Okay, so it's out. All right, well guys, look, if you stared at that long enough, you should realize there's something really cool. What's really cool? It's what? It's not 14? No, sir. Right, do y'all see that? There's two ways to think about this. Hey, guys, what is the inverse function to log base 10? It's 10 to a power. So what does log base 10 of 10 to a power do? guys, those go and annihilate each other, they undo each other, and you're left with what? Negative 14. Another way to do it, though, is like this. Guys, what can we do with that exponent? Does it apply to everything in that wall? Yes, which means we can put it in front. So what you have is minus 14 times log base 10 of 10. But what is log base 10 of 10? It's just 1, right? So think of it this way, guys. Log base 10 of 10 is like saying 10 to what power is 10? What is that? It's just 1. Hey, that's the one you got to know. No pun intended. So all that being said, does everyone see that what we would get here, okay, is a minus 14? Y'all with me on that front? But hey, hold on. Why then did they put in minus right here? Because they're just like you. And they don't like negative numbers. And they're like, screw negative numbers. Let's get rid of negative numbers. In fact, what we'll do is we'll just put a little negative right there. And so guess what that negative does? It makes it positive. Now we're happy. So it makes a nice positive 14. It does cause a one little issue, which means the more acidic that you go, okay, the smaller the value. That's also what that negative does. But anyway, that's okay, right? The point is, guys, that's where this comes from. So one way to think about the application of logarithms is it takes really small numbers or really big numbers, take the log of that bad boy, and you can bring it down into a much more manageable number. Make sense? Everybody good there? Okay. It does have a consequence, though. It has a massive consequence, right? So let me show you what I mean by that. And this is something that I need y'all to this has got to resonate with you, and this is true about anything that is logarithmically scaled. So by the way, real quick, can y'all tell me what is the, so if you have a pH of 7, then what is the concentration of H plus in a neutral solution? What is that?
10 to the negative 7.
Yeah, does everyone see? You can kind of pattern match here, and you get 10 to the negative 7. And then what do we have here, obviously?
10 to the negative 1.
Yeah, so 10 to the minus 1. Is everybody with me on that front? So here's the problem. And Tegan, I really want you to understand this. This is the problem with logarithm scales. Because, case in point, you can hold in your hand, and this is absolutely no problem. No problem whatsoever. You can hold in your hand a neutral solution, right? That's not going to be really problematic. And honestly, if I told you your pH is now 1, you go from a 7 to a 1, that doesn't sound too bad. It's not that much of a leap, right, to go from a 7 to a 1. But because it's logarithmically scaled, we have a bigger issue at play, and that is, well, let me show you. What does that actually mean? Well, if we looked at this as a ratio, right, so if you have a pH of 1, that means that your actual concentration is 10 to the minus 1. You guys with me there? What I want to do is, I want to compare the concentration of a pH of 1 to a pH of 7. I want to look at the ratio of their concentrations. So what I'm going to do is, we'll do 10 divided by 10 to the negative 1 divided by 10 to the minus 7. Are y'all with me on that one? Does that make sense? Can y'all tell me what is this equal?
Is it negative 6?
It does not equal 10 to the negative 6. It is 1 over 10 to the negative 6, but guys, that's just simply what? 10 to what power? Hey guys, if we bring our denominator up, that would be 10 to the positive 7. So 10 to the negative 1 times 10 to the positive 7. What do we do with those exponents?
You subtract them, so we 10 to...
No, you don't subtract them. You add them when you go up. All right, we're going to do it this way. We got to do it. 4-day weekend, man. Does everybody see you get that? So you add exponents. That's 10 to the negative 1 plus 7, which is?
10 to the 6.
Now, guys, what you're looking at here is really, really, really crazy. Because I know a pH of 7 to a pH of 1 doesn't sound that bad. But in terms of how much greater is that concentration, guys, it's 1,000,000 times greater, right? So another way stated, if you have a pH of 1 versus a neutral pH, it is 1,000,000 times more acidic. That's how much more acidic a pH of 1 is versus a pH of 7. That's the problem with logarithmic scales, is they hide the truth, really, right? It makes things sound like a really nice bump. All right, is everybody with me there? Does that make sense? So again, it's a million times greater. It's a logarithmic scale. That's the problem whenever we're reading pH and we translate it over to concentrations. We have to remember it's that way. I need you to know this equation for pH. This is one very common application. Everybody good on that front? There's one other common application that I think that you're going to see, at least in this class. I'll go and give it to you real quick. So that's one of them. And the other thing, guys, is the decibels, like how we think about, or how we measure sound. And so the way that a decimal system, it has its own equation, and it looks something like this. It's going to be 10 times log base 10 of, and I'm just going to write it this way, I divided by I naught. Now, what I naught is a reference intensity. So this is just a constant. That's all this is. This is just a constant. And this constant, everybody, is just 10 to the minus 16. So if y'all want to think of it this way, this capital I up here in this numerator, that's your input variable. That's the thing that changes. And this is sort of like your output. We call it the decimal. Largest stadium, the loudest stadium ever recorded, I believe, was the Kansas City Chiefs Stadium back in like 2012. But they recorded a sound, and I think this is not just NFL. If I remember serving around, I think this is worldwide. The loudest sound of any sports stadium occurred there at that stadium, which is actually pretty shocking. But anyway, Kansas City Chiefs did it in 2012, and it recorded. I believe, a decibels. So I'll just say it this way: Kansas City Chiefs. I think it was like 141 decibels. Here's what I would like for you to do on your own, real quick. See if you can do this. See if you can figure out what was the intensity of that sound. Go for it. What's the intensity of that sound? So here's your equation. See if you can solve out that equation. So one of the things on your homework, guys, I could very well just give you a decibels and ask you to figure out the intensity of sound, or give you an intensity of sound, figure out the decibels, right? So just using this equation, nothing crazy there. So what's the first thing you would do? All right, so you would set it equal to, oh, I see what you did there. Actually, I wouldn't do that. That is correct, and that's fine. You could technically do that. Well, I mean, you could almost bring your negative 16 down. I would actually do that too, and then undo that longer. Yeah, it would be a little swifter. What's up? Let's see what you did. Okay, notice, oh, I see what you did. Okay, so you split that up. That's fine. Oh, I love what you did. Cool. Cool. So divide up your 10. And then undo your logarithm. I would just divide your 10 over.
Okay.
And then undo your log. think is the first move that you probably want to make? Divide by 10. So guys, you should have 14.1 is equal to log base 10. Hey, eyes up here real quick. We don't need a fancy calculator here because we can actually just solve it out just like this. So what is the inverse? Who's the undoer? Notice that that's inside of a logarithm. We need the undoer of that logarithm. Who's the undoer? It's 10 to a power. So again, what you do to one side, you would do to the other. So what I want you to imagine is this. Again, this is what we talked about last week, right? So that's 14.1. Again, what you do to one side, we would do to the other. Sorry, I can't say speak. Does that make sense, everybody? Everybody good? Well, we now have just 10 to a power of 14.1, which is equal to I divided by I naught. Well, guys, what's I naught? Do you remember? That's your 10 to the negative 16. So what's the final move in solving for I? Yeah, let's move that over. And so if you did everything just perfectly, you'd have 10 to the 14.1 times 10 to the negative 16. And so, hey, help me out. What do we get there? What do we do with our exponents? Huh? Well, yeah, we're adding them, which that's a negative number, so yes, that does convert to that. So consequently, what do we get? We get 10 to what power? Sorry? Negative 1.9. And so, guys, that is the intensity of that sound. All right, everybody, does that make sense? Everybody cool? All right, do it one more time. But this time, hey, y'all ever been by a jet as it was flying like low or whatever or landing? You heard how loud that is? It's like freaking insane how loud a jet is. A jet, by the way, is giving off about 150 decibels. 150 decibels. Right? So, I want y'all to go ahead and tell me or figure out what is the intensity of that sound. Go into the exact same thing. So we got 10 to the minus 1.9 here. So hey guys, we're going to come back together real quick. Obviously, just set equal to 150, divide out the 10, raise both sides from a power of 10. Obviously, that gets us to here. Multiply both sides by 10 to the negative 16, we get 10 to the negative 1. So hey, I want y'all to look at this for a minute. So this is what I mean about logarithmic scales and how they can feel a little weird, okay? If you stared at this long enough, right, we've got something weird. You're going from 141 decibels to 150 decibels. That sounds like a small jump, right? Only 9 little decibels. But what does that actually translate to in terms of how loud that sound is? Well, guys, that's 10 to the essential, right? So that's about negative 2. That's about 10 to the negative 1. How much bigger is this number than that number, roughly? What would you have to multiply to this number here, guys, roughly, to get that number there? Uh-oh. Wakey, wakey, eggs and bakey. Come on. So just imagine that is about 10 to the negative 2. Hey guys, what do you have to multiply to 10 to the negative 2? Get 10 to the negative 1? 2. 10. Guys, this number is 10 times bigger than that number. So what does that mean? Even though we went up and 9 decibels, it doesn't sound much. That's huge. That literally translates to 10 times louder. The loudest stadium on earth still was 10 times less loud than a jet taking off. That's how loud 150 decibels is, which is pretty crazy. Does that make sense? So just a little 9 decibels. I want you to remember that because of this. What is the loudest sound? Some of you know this because some of y'all are nerds. What's the loudest sound a living organism can make?
A whale.
It is a whale. And in fact, I want y'all to notice this. This just blows my mind. So guys, it actually turns out to be the sperm whale. The sperm whale and its clicks that it makes, those clicks. Any idea how many decibels those are?
1,000.
Hey, remember, a jump of 9 is a multiple of 10. It's 220 decibels.
So, we try that.
That's mind-blowing. Mind-blowing. Like, in terms of how much greater that sound is. In fact, just to kind of put that into perspective, here's a jet taking off, here's a sperm whale. So check this out. Let's just put a little 220 right in there. Obviously, if you did that, that gets you 22. That puts a 22 right there. Obviously, that's 22. That becomes a 22. Guys, what's 22 minus 16? I believe in you.
6.
It is 6. You did it. But that's a positive 6. So putting that over here, I want y'all to notice what that gives to you. If you are 220 decibels, this is a mammal. This is a mammal. It is literally 10 to the 6. Guys, how many times bigger is this number than is this number than that number?
7.
No.
710.
No.
700.
A bazillion.
700, no.
A bazillion.
7 million.
Guys, how many?
7 more zeros.
10 to the 7. There's 7 more
7 more
zeros. Guys, it's 10 million times. So guys, a jet taking off, a sperm whale's clicks are 10 million times louder than a jet. Mind-blowing. I mean, that's cool. I don't care who you are. That's cool right there. Right? That's just mind-blowing that an animal could produce that kind of a sound. All right, let me show you what a semi-log plot is, just to kind of preface it. So here's some data that Shane and her group from AP Chem did earlier in this year, and where it came from and all of that doesn't really matter. What I want y'all to notice is that we have data, and it's clearly not linear. Would you agree with that? It's clearly not linear. Okay. A semi-log plot is actually not anything too crazy at all. Here's what we're going to, hold on. So here's what we're going to do in a semi-log plot, right? Is I'm going to come over here and I'm going to take the log. So in fact, I'm going to do, most of the time we'll do log base 10. For reasons I can explain at a later time, but I'm going to do log base 10 of this data here. And if I did that just perfectly, I'm going to bring that on down. There we have it. So I have now taken the log of the data. So what do y'all think is going to happen, right? If I plot this alongside this,
It's going to become linear.
I have a sneaky suspicion it's going to look a little linear. Now, I want to make sure that we're clear, guys. All I did, and this is where I need your brains on, all I did was take the logarithm of these values here. Everybody with me on that front? I took the log of those values. And so again, if I were to actually look at that graph, what do y'all notice about that wonderful graph?
It's linear.
Yeah, it's actually very linear. Now, that tells us something that I'm going to mention in just a minute, but this, what y'all are looking at here now, is actually no longer what we might consider a normal graph. This is a semi-log graph. Now, what does semi-log plot mean? A semi-log plot, guys, just basically means if you have, so I'm going to come down here and say it this way. So what's normal, right? Normal would be, we plot y versus x, right? In a semi-log plot, here's what we're going to do. We're going to do the log of any base, really. It doesn't really matter your base, but most of the time it's log base 10, okay, of your y values versus x. I literally just go through and I take the log base 10 of all of my y values. Are y'all with me on that front? There is another way to do a semi-log plot. So you can either do it that way, Or you could do it this way. You could do y versus, and then we could do the log base 10 of our x values. This is a little less common, but it certainly is well within the realm of doing a semi-log plot. So that is a similar log plot. I'm not going to cover it, but what do y'all think a log plot is?
Log of x and log of y.
Yeah, so both x and y have been escaped. Is everybody with me there? 100%. Okay, here's the deal, right? I want to show you why, oh why, this would ever happen, right? So first off, why would we ever do a semi-log plot? So what is the purpose behind all of this? Well, guys, because I'm hoping for linear. Or, you know, just like y'all see on your screen, the only reason I'll ever do a semi-log plot, guys, is if it produced a linear graph. Are y'all with me on that front? Does that make sense? Addison, was that a sneeze?
Yeah.
That is wrong. Y'all didn't hear that? No. Right? I know. All right, I won't get distracted talking about Addison sneeze, but I mean, that's really interesting. A little silent sneeze out. All right, hey guys, here's what I want y'all to realize in a semi-log plot. And I'll show you some of these in just a second, but suffice it to say, it's pretty straightforward. Now, why would we ever do this? Well, I want to show you something. Here's the deal, right? The reason you saw that it was linear on that last graph was because the original data, you remember how it was curved? Everybody moving there? It was originally curved. It's because it was actually exponential. So if you have an exponential data set, and you do this semi-log plot, which is a fancy way of saying, let's just take the logarithm of my outputs, but the logarithm of my outputs predominantly is the one we'll do, right? What that's going to do is create a linear relationship every time, which is honestly just easier for us to deal with. Everybody with me on that front? So, if you go back to the pH scale for a minute, did y'all notice that the only thing changing in the pH scale is what? Like when we were looking at all these different, what's the only thing that's changing here? It's the exponent. So what am I telling you? Guys, I'm telling you that secretly, right, concentration, if you were to plot that, guys, that's going to be exponential. That's what I'm trying to tell you, right? It's 10 to some power. That's what it is. So then if you take the log of that, if you take the logarithm of that, it undoes the exponential, and you're left with a linear relationship again. You get what I'm saying? Does that make sense? And so a pH scale is linear. But that's only because this guy here is, of course, exponential. Everybody good there? All right, so just to kind of prove this to you, hopefully this makes sense. So guys, if you have some data set, every exponential function on Earth can be written in what form? That's right, so you have a times b to the x. So, so just to write, this is obviously if you have some exponential function. I know I'm doing a very ugly drawing, but right, if you have this relationship, and guys, over here we're plotting x, over here we're plotting y. A semi-log plot would be, if this is x here, well now I'm going to plot the log of my y values. Does that make sense? I'm going to specifically choose log base 10. And this, yeah, so just log of y. That's what gets plotted here. So what happens to this curve in a semi-log plot? What does it do? It becomes straight, becomes linear. Make sense? Let me show, so I'm going to prove that to you. At least hopefully I will. So here, imagine guys, if you have, obviously, our exponential, which is a times b to the x. So watch this. Here's what I want to do. Here is our wonderful exponential. Whoopsies, that is not our exponential. So imagine you have a times b to the x power. What am I taking the logarithm of?
Y.
Just your y values. Is everybody with me there? Okay. I would rather you not write what I'm about to write in your notes. I will tell you when. I would rather you just stay with me through this, okay? Y'all are doing great. I'm almost done. So, hey, we're going to do the log base 10 of both sides of this equation. So, right, we're going to, what you do to one side, I want to see you do to the other side, okay? And so, obviously, we're going to have a y here, which is equal to a times b to the x. Okay. Well, guys, on the left side, you'll notice that's what we're plotting on this axis, on this semi-log plot. So there's nothing else that we can really do there to clean that up, so it just stays put. But can y'all imagine something, a cool property of logarithms that we could do on that ladder, on the right side of that equation? Do we get to bring the x down first? Good job. So hey, I want you to notice that we're going to get a log base 10 of a plus, obviously, log base 10 b to the x. Well, what can I do here now? Yeah, let's actually move that x to the front. And then here's what I'm going to do collectively. Would y'all agree that 3 plus 2 is the same thing as 2 plus 3?
Yes.
Order doesn't matter in addition. So I'm going to flip-flop those two bad boys. Make sense? Okay, so coming over here, you're going to love this screen, I think. So right, we're going to have log base 10 of y, which is equal to, all right, check this out. We're going to do, so like I said, I'm going to flip them. I'm going to bring my x down, so there it is. That leaves me with log base 10 of b, so there's not really anything over there. And then we still have plus log base 10 of a. How we do? Make sense? Which if you stared at that long enough, you might notice something off. Right? Because isn't log base 10 of, well, whatever the base is just a number. So what's log base 10 of your base? Well, guys, if base is just a constant like 3, pretend it was 3, then what's log base 10 of 3? Just a constant. So if you don't mind, these are multiplication. I'm going to flip these. So now what we have here, Calamani, log base 10 of b. So then I have times x. I just flip those. And I still have this guy hanging around the park. Now, guys, remember, a and b are just constants. So if you really squint it, like you, my 4-eyed people, take out your contacts, right? Take off your glasses. And you squint it that long enough, you might know something really cool. Number one, would y'all agree that's just some number? Right? Let's just call it m for kicks and giggles. Okay? I don't know. Just some number, we'll call it m. We still have the x, of course. Right? Would y'all agree? I don't know what a is, but log base 10 of a is just what? Just some number. I don't know what to call it. I'll just pull something out of my hat. We'll just call it b. Oh, that thing is linear. And guys, what I just proved to you is that it's always, obviously, guys, logs undo exponentials. And so what would you get then under this new thing, right? Well, guys, you would obviously have a y, remember b is your y-intercept. So if you wanted to, you could think of this as being log base b of a. That's your y-intercept. This is going to increase or decrease depending upon if you have exponential growth or decay. Your slope is what? What's your slope equivalent to? You'll see this on your homework. It's what? Yeah, log base 10 of your, log base 10 of your original base. So you're putting it all together. Well, guys, what's what I need you to get from this, okay? Here. If you haven't listened to me all day, this is your moment. If you have exponential data, you take the log of your outputs of that data. What do you expect to see? Simply linear. That's it. So if you haven't jotted that down or your brain's not there, guys, write that down. That's huge. If you have exponential data, you take a log of that data, well, guys, it's going to produce a linear relationship. Everybody with me on that? That's what I just basically proved for you. You're guaranteed to get a linear relationship in the semi-log plot. Would y'all also agree that this is only true for exponentials? Guys, if you have tangent and you decided to do a semi-log plot, ergo you decided to plot log base 10 tangent, oh hell no. That's not going to get you linear. right? That's not going to look like who gives you linear is it's got to be exponential, which is because what if I gave you data that was you already like I guess I'll say this way. We can almost use this as a test for exponential, because if I take a data set and I do the log of my outputs, plot it, I do get linear. That tells you your original data set is 100% exponential. Everybody good on that front? Make sense? Mind blown a little bit? Everybody cool?